Okay, so let me now study the properties of these modes, Fourier modes of the density. Okay, rho n. So I remove the plus and minus which correspond to two branches. Okay, and let me study these properties. So first of all, I want to stress that we did this subtraction of infinity, and this is unambiguous. So if somebody tells you in your life that normalization is something unclear or not well defined or murky thing, you should say, no, it's completely clear and completely well defined. You are wrong, okay? So let's make this strong point, okay? Okay, here is defined by these conditions, and then the subtraction makes sense for studying the charge is not the charge of everything, it's just the charge of excitation around the Fermi surface. Okay, around the ground state. Okay, okay. So rho zero will measure the. Okay, so what is then property on the ground state? So rho zero on ground state makes zero by definition. So I remove the normal ordering. I remove it because we understand it has been normalized. So rho. So rho n on the ground state make zero for n bigger than zero. Okay, because I said that rho n makes a jump of minus n. So and on the ground state, it can start to act when it is one state is filled, but then it goes down, it is filled, so it makes zero. Okay, so this is zero. Instead, rho n omega will produce an excitation for n bigger, lower than zero. Okay, because you will do this. Okay, for n negative, we will do a jump above particle excitation with momentum delta n. Momentum, okay, or momentum number delta n. Okay? Okay? So what is the algebra of these operators? Okay. Here you have to do a calculation. Okay. Well, I skip one step because it's trivial. So sorry, C, not C, not B. I skip one step because it's obvious. Okay. So I get delta K L minus M B dagger K minus N C C L minus delta K minus N L B C dagger L minus M BK CK. Okay. Okay, if I now shift, I started with N and M different from 0. So this normal ordering does not affect these operators. Okay? No problem normal ordering. But, okay, so you would say this is 0 because I simply shift, you see, if I take if I rename this k prime equal k, you say that k is equal to k prime plus m. Here I make a substitution, then it cancel out. Okay, that's fine. But the point is that if m is equal to, so this is in general, but for n m equal to minus n, okay, I'm going to get something which is, you see, ck and ck. And then I have to rewrite this ck, c dagger k into the normal order form because I want to get a result in terms of normal order operators. Okay? And this is a problem because, so I'm going to get for m equal to minus n, I'm going to get something proportional to CL. Okay? And I don't want to replace this CL by normal order of CL. And this normal ordering, I cannot do a shift of index because normal ordering is not shift invariant, you see? Depends on the index here. Okay? So there is a mismatch here. And so let me evaluate this case in particular. I may continue here, maybe. So rho n rho minus n is going to be sum over k c k minus n c k minus n minus sum over k ck ck. Okay? Okay? So if I want to replace with a normal ordering, I have to do this subtraction here. Okay? And so I get the following factor, sum over k minus n less or equal to 0 from here, plus normal order of CC, minus sum over k less or equal to 0 of 1 minus CC. Okay? Okay? Okay, these at this point, these cancel each other, but they remain this mismatch of subtraction induced by the normal ordering. And this is sum over k equal to 1 of n, which is n. Okay? So I have shown you that rho n, rho minus rho m is n delta n plus m 0. This is called current algebra. Of course, here also, because it's a math argument, the numbers are abundant. The names are abundant. So you have, it's also called Kac-Moody algebra, affine algebra, also line bundle, not line bundle, sorry, affine bundle, but nevertheless, let me use current algebra, okay? Okay? So, okay? Okay, now you say, well, you did some dirty trick here. No. No dirty trick here, okay? So let me do another argument, okay? So it's all given once I specify these ground state properties. No dirty trick. Okay? Okay? Let me compute the following quantity. Rho n, rho minus n omega. Okay, notice in passing that this is a norm. So this is like rho norm or rho minus n omega modulo square, because rho n dagger is rho minus n from the definition that was somewhere here. Okay. 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 So let's do it. Okay. From the definition, you see, because of this property, this can be replaced by a commutator. Because the other way around is 0, okay? And also n is bigger than 0, okay? Then it is a simple exercise to see that this is, by definition, written in terms of this operator, okay? Sum over k, ck minus n, ck, sum over l, ck l plus n, cl, okay? Okay? And now you see that you use these other conditions to see which terms are different from 0. And there are corresponding, by conjugation, there are corresponding expressions, okay? ck and ck on the other side, okay? Okay? Now you see they will be left with just a finite number of terms, and that will give you n omega omega. And there is no ambiguity here in this calculation because this does not use normal ordering, because n is bigger than 0, so these are not affected by normal ordering. Result, however, is non-zero. Of course it's non-zero because it's a norm of a state, it's a norm of excitation. How could it be 0? A state, the norm of a state which is an excitation, okay? And okay, going from here to here, you feel yourself, but it's very simple. Okay, this requires that L is bigger. If you apply this, okay, it requires that L is bigger than 0. Okay, and this requires that K is bigger than N. Okay, positive. And then you start to find the terms which are possible. You commute, and then you get the final sum, okay? So there is this fact. So this is this coefficient n. Oh, okay, I did it. I redid it in my notes because I wanted to be sure. But okay, you can do by yourself. So what is this n here? This is the anomaly. This is the effect of the anomaly. You know, because it's coming from regularization. because if I didn't have to do this normal ordering, I would get 0. Okay? So in some sense, the anomaly comes from a regularization of the Dirac sea. Okay? So the technically is effect of the infinite Dirac sea. I have to do this normal ordering procedure. But physically, this is nothing else that low energy property, because these are for finite n. These are just telling me what is the behavior, what is the behavior of particle excitations. Okay, so physically is an infrared effect, but technically in the relativistic theory is coming from normalization. Okay, so now let's see that you come to derive again the anomaly that we knew already. Okay, and it goes as follows. Are you following? Yes, please. Rho minus n, yes. Here. Rho dagger n is rho minus n. Minus n. This is minus n. Yes? Okay. So, are you following? Huh? Too fast? Okay. So, not all lectures can be as good as the first one. Then you start to decay. It's I mean, human. It's human property. Yes? Huh? We here? Uh-huh. Yeah. Okay, so let's get to the what we knew about the anomaly. Okay, first we rewrite the commutation relation of modes in terms of densities, and the result is the following: rho of x, rho of x prime is equal to minus I over 2 pi dx delta of x minus y. How do I get this? Well, I first have to invert the Fourier transform. So rho n was dx e to the minus nx over L 2 pi rho of x. Okay, so that means that rho x is 1 over L integral, sum over n e to the I 2 pi m x over L rho m. Okay. Okay. Then I compute this by taking this. Okay. So yeah, it just to show that this is nothing else that 1 over L sum over m. Okay. Now let me do like this. From this to this. Okay. So okay. 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 On the other hand, this is also equal to 1 over L sum over M e to the I 2 pi x minus x prime M over L times M, which I can also write 1 over L sum over M and N e to 2 pi xm plus x prime of N delta M plus N 0 M. Okay. Okay. And so this is the Fourier transform, you see, Fourier transform of this commutator in terms of this. Okay. 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 So now with this property, we compute the conservation of charge in each sector, in each of these branch. Okay. So what is the coupling to the gauge field, where you change the Hamiltonian by adding the dx j mu mu. Okay. If I put a x equal to 0 and a 0 equal to minus x electric field, which I can in 2 dimension, this is going to be h plus dx rho 0 plus rho 0 minus h0 with this h0. Okay. Now I'll compute. Let me compute first for the plus thing. For the plus thing, I can do the Heisenberg equation of motion. Okay. Okay. This is going to be rho 0 plus of x commutator of h0y rho y. Okay. Okay. So I use the commutation relation. I get 1 over 2 pi dx, dy, dx, dy, a0 of y dx delta x minus y, okay, which is 1 over 2 pi integral of dy ex of y, because I transform this in dy, okay. I act by minus dy, I act on this other side, and I get this. Okay, so there is an anomaly. The charge is not conserved for the first branch, so plus. Okay, which is what we know. We produce with an electric field. We make this spectral flow, and you go up above the ground state. So what happens for the other branch? The other branch, rho minus, because of the fact that the index n is reversed, no? Because n was proportional to momentum. So instead of, I just cancel, instead of the ground state condition of before, they are reversed. N goes into minus n, okay? So for the other branch, you get a minus sign here. So you get a minus sign, okay? So you get for, so this is Q plus dot, Q minus dot is minus this. Okay? You get a minus sign in the commutator, and you get a minus sign. That means that the charge is diminishing because they move in this other way. Okay? So the total charge is conserved, but the difference of charges is anomalous. Okay? And so you recover the anomaly of that we discussed before. Why it is an anomaly? Because in the classical theory, as I said, each individual charge is conserved. Okay? While with the action of the gauge field, only the sum of the charges is conserved. But the difference of charges, okay, is not conserved. That was what is called anomaly. Okay? So this result here is the anomaly because it produced this delta prime commutator relation, which produced the dependence on the electric field. Yes? Because the current is rho zero, rho. It's just a naming, okay? So J mu is J0, J1. And J0 I also call rho zero because I'm kind of perverse. Mm. The notational convention, okay? Sometimes you find alpha n. This is another notation. Okay? Well, in fact, there is another thing that maybe is important, but maybe you don't realize now. Is that you can define other objects in the theory which are kind of interesting, which are the energy modes. maybe you remember that in the Hamiltonian there was this piece. So this piece is in the Hamiltonian, okay? So this is the Hamiltonian, the part referring to the plus branch. So in particular, L0 is the Hamiltonian, okay? So it's a Hamiltonian density, okay? So L0 is the Hamiltonian. Okay, let's use, okay? Hamiltonian. But it's also interesting, so there is a spectrum, okay? Okay? You can work out what is the spectrum. For example, you will find that the energy, but I don't say this. You can work out the spectrum from this. But what is interesting is the algebra obeyed by these operators. I mean, you can do the same thing as before. The only point is now instead of having C dagger C, you have also a coefficient here which depends on it's linear in K and N. Okay. So repeating the steps, you can compute the commutator and discover that there is an additional piece due to the anomaly, like this, due to the normal ordering that also apply here, okay? Because L0, again, L0 will be, you see, L0 will just count the energy of all level. L0 is just K minus 1/2, which is the energy of, in units of the energy K is K minus 1/2 2 pi over L is the energy of each mode. It will count the energy of all the states in the Fermi sea. Okay, so again, this has to be should be redefined by normal ordering, such that L0 on the ground state is 0. Okay, it would be the energy of the ground state is normalized to 0. Okay. So you need the normal ordering. You can do the same calculation as before, and you will get the following. The algebra is the following. And also there is the algebra of the L with the rho. So these are two pieces that add up to the current algebra, and this is called Virasoro algebra. Okay. And the meaning of it is that it realizes transformation of space which are conformal. So transformation which are transformation of space which respect the angle between vectors, but deform the vectors and deform the space by keeping the angle between two vectors fixed. I mean, we will return to this if there is time, but just to know, to tell you that this is very simple consequence with the same steps. Okay, for example, this is a consequence of the anomaly, and has another name. It's called conformal anomaly. Okay, but it's the same effect. Is effect that of normal ordering in the ground state, and in fact you can compute by again by like this, by doing this simple calculation. You try to evaluate ln L minus n omega, okay, for n bigger than 0, and you will discover that you will get here L0 because n minus m 0, so that makes 0, and so you will get this coefficient as a result. Okay? So just this is to say that the so-called current algebra is made of three pieces. Is made of the algebra obeyed by current modes, and also this, and also the algebra obeyed by the energy modes, the Hamiltonian density modes, okay, and the mix correlator. Okay. Do you have questions? So maybe we stop now because we switch to another subject. Today is a tough day, 4 hours. Please. Yes? It is a conformal theory. Yes, yes. So this is it. This is a conformal field theory. It's conformal invariant, and there is a conformal anomaly, which has the same origin. And in general, this is a term. In general, here you have a free coefficient C, which is so-called central charge. And in this special theory, it is C equal to 1. Okay? Yes. So what can I say? Well, why it's called a central charge? Because it's an extension. I mean, you have a classical algebra, which is this 0 and this without this piece. This is a classical algebra. Then you say, is there a possible to extend this algebra purely from mathematical point of view? Extend the algebra with some operators, which is just a constant, or if you want, commutes with all the other operators, it's just a constant, respecting the Jacobi identity, which is an identity obeyed by all the algebras. You will discover with this structure then the possible extension, central extension, are this in this case and this in this case. There is here you may add a piece, but by proper definition, you can remove. Okay? And so these are what I call this central extension. Central element is an element that commutes with everything. Central extension. And that's why it's called central charge. Yes? Yes, the same. The same. This doesn't change with a minus sign. No electric field, yes. Yes. The effect of the field I computed there. Yes. No, because the field in principle depends on position, so you lose translation invariance. And in general, you cannot really solve completely, but you can compute something because we are in one plus one dimension, and you can compute a lot of things. But in general, for arbitrary constant electric field, of course, we computed before. But in general, backgrounds, no. Anyhow, yes, please. Why is C equal to 1 and not 1 half? I mean, we built it just from one component of the spinor, so that's 1 half. No. It's C for one component and C from the other component. It's 1, 1. Yes. In principle, there is also a C here. If you're a more general theory, you also have a C here. But then there is this plus minus depends on convention. So don't go. No, let's not go into much detail. Then it's a matter of convention. So you just compute. You know that in general, this is a term that you have the possible structure of the terms you can put in order to obey the Jacobi identity with these three parameters. So that gives you all the possibility. But then you compute by doing this calculation here. You compute. You can do, but as an exercise, it's not difficult. You compute and then you find 1. So that's it. And if you do for the other, you also find 1. Okay? please. Yes. Yes, there is something else which is not conserved. It's a stress tensor conservation. But this is getting okay. For your record, okay, you keep in mind the formula, okay. There is there is another symmetry which has to do of the free fermion theory. There is another symmetry which is associated to space-time, and if you put the system in a background, okay, so you have to imagine that you promote your theory to a theory which depends on the field, but also depends on some two-dimensional metric, okay, okay, and then there is this. And then there is the stress energy tensor T mu nu, and of x, and T00 is the Hamiltonian density just said. Okay? Okay, so what is the definition of the stress tensor? Is the variation of the action with respect to the metric variation. Okay? So if you have such a theory, you have a diffeomorphism invariance. Which is the or general coordinate invariance of general relativity. Okay, you promote a theory to a theory with a background, and you impose that the theory is invariant under general coordinate transformation of diffeomorphism. Okay, which is x mu that goes into x mu plus epsilon mu of x, invariance of the action. Okay. This implies that in this case, in this special case, this becomes d mu epsilon nu symmetrized, or if you want. Okay, so this is a special case of transformational metric corresponding to general coordinate transformation. Okay, so out of this you get that you have another quantity which is conserved, which is a stress energy tensor, which is d mu T mu nu equal to 0. Okay, and okay, this is another symmetry you have in the classical theory, which is broken by chiral symmetry. Okay, is broken in a chiral theory, or actually in any theory is broken. So this anomaly is not necessarily related to fermions. Okay, and the formula is that this is different from 0, and the result is d nu, or say c over 12 d nu r, where r is a scalar curvature. Okay, so this is another anomaly, and so this anomaly, this C is the same C which appear here. I would love to explain you, but it requires another hour, so next course, otherwise we go into the wrong direction. Okay, so this has okay, if I have time, this has physical consequences that I may tell you, because I wrote a paper on this. This is related to not to the electric current, but to the thermal current. Okay, thermal current. So there is an effect on the thermal current. Well, why it is so? Well, I mean, there are several ways to see this. It's all in my review. Is explained in very detail. Okay, the simplest argument is that while electromagnetic field coupled to charge, quindi coupled to charge excitations, the metric couples to all matter, charge and neutral. So when you deform by adding a metric, you produce a current of all the excitation you have in the theory. First statement. Second statement is that, in fact, I think due to Luttinger, if I remember well, Luttinger, show that you can represent a thermal gradient, so a difference of temperature in a theory which has no temperature, as a difference of gravitational potential, which is contained in G00. Okay? Remember, G00 is something like 1 plus some no, some gravitational potential, no? Some gravitational potential in the relativistic limit. And so with this gravitational potential, you can represent the difference of temperature. So you can put the system in some thermal, you can change the temperature of the system by putting the system into a background. And then this formula will produce you a current, okay? A momentum current, because you know that P mu is integral of T0 mu. You will have a current which is momentum current, which is different from zero. Which is in fact has been measured. Just okay. So we have a break for another hour. Sorry for this. So now we are going to describe application of chiral anomaly in the quantum Hall effect. So how many people know what is the quantum Hall effect? Okay. How many people know what are the Landau levels? Great. Okay. So I will try to be short because this is also a very long story, and let's see. Okay, so first of all, so everything started with an experiment. Okay, experiment. So I think 1980, von Klick experiment. So the origin is experimental, and so let me say a couple of things about this because I mean for history, okay. So basically, the whole effect is when you have a two-dimensional electrons. For example, you have a conductor which is planar, okay. You can realize this by allowing electron to move freely in a certain layer of semiconductor, no? That you, according to how you make a kind of sandwich, and electrons are this z. They can move in x and y like this freely, okay? Then you put a strong magnetic field B, and you know what is the is a classical Hall effect, no? You put a different some potential here, let's say. So you create an electric field along Y, but the current flows along X. Why is that? Well, classically because you have a Lorentz force that bend the electron, okay? Maybe it's like this. They bend the electron while they start to move. They bend them, okay? And so the current finally is in the opposite direction. So you measure a current which is orthogonal to the applied electric field in the plane due to the presence of this magnetic field, okay? So the experimental result is that, of course, you have a resistance, you have a conductance, okay? The conductance, so normally you have J is proportional to, J is equal to sigma electric field, okay? And J has index I, and I is x, y, is in two dimension, okay? But then there are, in general, you have a longitudinal current. This is ohmic conduction. But this is a different current. This current is orthogonal to the applied electric field, okay? And so there is, in fact, this sigma ij is a two-dimensional matrix. In some cases, it is zero, the conductance, the usual conductance, but different from zero, the orthogonal conductance, okay? Why I use the conductance? Because this formula is intrinsic, so independent of the detail. So you have to imagine that you take the system, then it will have a certain dimension and certain resistivity, conductance. Then this I take the density. No, this is the current density, and not charge, and then I have electric field. So this is free. This quantity conductivity is free of geometrical details. Okay, and the result is that in certain cases, the ohmic conduction disappears, and the value of sigma h are very precise, and they are e squared over h n, where n is an integer. This is integer or effect. Okay? So this is a quantum effect because, okay, you have a h bar here, h, okay? And also, in general, you wouldn't expect this property, so it's a quantum effect. But a remarkable thing is that the precision for this value is remarkable. So this is truly an integer number. So when the measure, you have the error, or sigma h divided sigma h is 10 to the minus 9. Okay? In fact, now they use this value for metrological applications to establish some fundamental, you see, it's written in terms of fundamental thing. So that you start to say, oh, there is something special here, because how could it possible that a piece of material, well, it is a very low temperature, so it's a very peculiar situation. You have, temperature is about 1 Kelvin, and very strong magnetic field. How is possible that such a piece of vulgar material produces such a precise thing? Well, the reason is that because this n is related to the n we saw before of the monopole quantization of first gen class. Okay, so my goal would be to let you have some flavor of it, because it's a long story, but we try to do this. Okay. So the result, and so that's a quantum effect. The fact that you have a response of the system which is exact and but basically exact. So it's there are no corrections to this thing, is the starting point of this field of topological phase of matter. So the field started in the 80s, then it went on in the 90s, and but then there has been there was a shift around 2010 when people understood that this property of the quantum Hall effect, which looks kind of peculiar of low temperature, high magnetic field, so very quantum regime, are also present in other material without magnetic field and without these complications. So, and then many more systems, which are called topological materials. Now we search topological materials in the archives of all the compounds which exist in Bilbao, in Spain, okay? And they believe that possibly 10% of the all stoichiometric crystal or material could be topological. I mean, less than 10%, but then eventually where they really are is not clear. But there are many examples of topological materials, okay? Okay, so that's more or less the story. And so let's try to understand. What I want to show you now is that in fact you can consider another geometry which is more convenient, which has a rotational symmetry, which is a kind of an annulus. Okay. Okay. And what I'm going to tell you that this all current is related to the anomaly, to the spectral flow. How is this possible? Well, first of all, we have to study this current in this geometry. So we will put a magnetic field, okay, B here, okay, and then we will make a electric field in this direction, and observe a current which is so in the theta direction, or you prefer to call x, which is r theta, okay, or r phi, let's say, okay. And you will find instead the current J, which is in the radial direction, like this. Okay? So the whole current will be the fact that given this magnetic field, you put an electric field in this direction, tangential, you will get a radial current. Okay? The main point of my argument is that it's going to show that in this situation, you will have an electron here, which have a big gap. Okay, so here there is a gap delta proportional to B over the mass of the electron. Big gap. So inside here nothing moves. Instead, on the boundary you have one-dimensional electrons, which are chiral. One goes in this direction, and the other goes in the other direction. On the boundary you have massless chiral excitations. So somehow I'm going to show you that the spectral flow, which was, you remember, the fact that they move like this on the two branches, okay? In fact, these branches will be realized not in momentum space kappa, but in x space, and there will be a branch here and another branch here, okay? Chiral but separated. And so this current will be exactly the difference of charge, change of charge between the two things, which is the chiral anomaly. Okay? So that's the setting. Okay? Please. Yes, yes. So in fact, there is the same story that we show you. On top of the magnetic field that is there, okay, fixed, constant, large, you will have to add the flux here. Phi, this flux sensation depend on time, such a way that, okay, d to dt of flux is equal to integral of electric field in dx on the boundary, yes. Yes, so precisely that thing. Okay? Then the non-trivial thing to understand now that is that in this system you have these two chiral, the fermions split in two chirality. The two chirality are separated in space. And one is taking place on one boundary, and the other is taking place into the other boundary. This is a piece we are missing, but then the rest is fine because we understood the spectral flow. So what is a spectral flow? Well, the electrons will move like a, you know, like a, a, a stream of ants, and then little by little they move and they reach the other boundary, and this is the current. Okay? Okay? So to get this, you need to do a number of steps. First of all, to know that what are the Landau levels. Okay? The Landau levels is that you have to solve the Hamiltonian in 2 dimensions, which is okay, with a gauge field which is fixed gauge field, which is minus x2, x1. Okay, so that the magnetic field associated to this is B in the third direction. Okay, the third direction. Okay. Okay, if you work it out this by knowing that P is minus Pi is minus I di, okay, you have to work this out. You will discover that the Hamiltonian can be written in terms of harmonic oscillators. Okay, first of all, I put the mass equal to 1 just not to bother. Okay. And also, I put also the magnetic field equal to 2. I will explain later why. Yes. And so this is going to be where these are oscillators, and the system has a rotation invariance, and so because I choose this geometry here, okay, has a rotational invariance, and the angular momentum is going to be written as where in terms of another pair of harmonic oscillators, which is like this, and A and B commutes. Okay? So what is the expression of A and B? Well, you know, this is derivative, this is linear, so it's a linear combination of derivatives and coordinates. One has to work a little bit, which is this page, okay, and discover that A is equal to, so A is a number, okay, so is d bar by L, no, sorry, L d bar plus z over 2L, and A dagger is z bar 2L minus L d, and B is z over 2L minus d bar L, and B dagger is z over 2L plus d L. L is a unique length unit of length, which is called magnetic length. Okay, which is 2h bar c divided by EB. Okay, while omega c is B over m. Okay, so because it's a unique length in the system, in this Hamiltonian. Okay, I can put m here at this point. It doesn't matter. Okay. Yes, and then if I put this equal to 1, that this implies in units in which I put everything to 1, also b is equal to 2. Okay, so this will be 2. I mean, it's possible to do this because in case at the end I will be able to recover all the dimensions. Please. Yes, yes. These are these. I'm going to say yes. These are derivative with respect to complex coordinates. Okay. What are they? So okay, z is x1 plus I x2. Okay. Z bar, you know. Okay. And then derivative is obtained by saying that the dz of z bar of z is equal to 0, and dz of z equal to 1. Okay. And so d is going to be 1/2 d1 minus I d2, and similarly for d bar. D bar is complete conjugate. Okay. Okay, the spectrum is very simple because you see I have like a one-dimensional oscillator, but in fact it's like a two-dimensional harmonic oscillators. There are two harmonic oscillators for the two direction, but in fact the energy depends only on one. Angular momentum depends on one. Okay. So I can define the harmonic oscillator basis, and I discovered the following, that I have wave functions. I can obtain states, wave function, which depends on index n and l. No, maybe I call it m, where this is energy, which is 2n, and this m is angular momentum. No, I have to put, otherwise I confuse with the current, sorry, angular momentum, m, okay? So how do I make them? Well, very simple, because it's, you start from the ground state, with empty ground state, then you put a dagger some power n divided by square root of n factorial, and b dagger m divided by square root of m factorial. Okay? So this is not the state nm. Okay? These are all the states. And as you can see, n is greater or equal to 0. And then by studying carefully the condition, you will also find that m is bigger or equal to minus n. So what is the form of wave function? That's what interests me more. Okay. So what is the spectrum? The spectrum is I can put it like this. So here I have angular momentum m, and I have the so-called Landau levels. Because this is n equal to 0, this is n equal to 1, and the energy here is 2n plus 1. Oof. Okay, and then I have angular momentum. So I start from 0, 1, 2, 3, 4, etc. This starts from -1, 0. First, this is called these degenerate levels are called Landau levels. Okay. Okay, and okay, the energy is proportional to B. So this is big distance here. Okay, but in terms of angular momentum, they are degenerate. Okay, that's the Landau levels. Okay. Okay, the Landau levels, yes. So what is the form? What is the form of the wave function? So because I have temperature much lower than omega c. Okay, I'm interested mostly in the lower Landau levels. I mean, not very high. Okay, in particular, I want to study the lowest round. Just to start, let me discuss the lowest Landau level. Okay. What is the form of the wave function in coordinates? Because this is formal, okay? Well, the form of the wave function is of the lowest Landau level is a ground state, a wave function of n equal to 0, m of x equal to 0, because it's the lowest state. Okay, lowest state is as a function of x. This is d bar plus z half function of z and z bar equal to 0. Okay? And what is the solution? Solution is phi of m 0m is e to the minus z z bar half z to the m. Okay, because the solution of this condition. Okay, so this piece is annihilated by this. Okay, that's fine. Then I'm left with the analytic function, and this analytic function should be an eigenstate of angular momentum, which is in coordinates is in coordinates this is z dz zd minus z bar d bar. Okay, so this is a generic analytic function, but in order to get eigenstates of angular momentum, I have to put a power, because z m angular momentum applied to 0m gives me m 0m, okay? Because this is z dz applied to z to the m makes m, okay? So I have found the form of the wave function in the lower Landau level, okay? Well, you know, that's not a great deal, because these are just the wave function which are in classical semi-classical motion. No? What does a particle in a magnetic field does classically? Well, it wings, okay, like this, okay, and so this function, in fact, is peaked around a certain radius. You see, so phi m modulo square is e to the minus r square r to the m, okay, and it's peaked. This is r is square is z bar z, or x1 square plus x2 square. Okay. This is picked for r square equals square root of m. Sorry, r square equal to m. Okay. So you see, this wave function, they make a kind of onion type structure. Okay. In the lowest lambda level, they have this. They all have zero energy. Oh, sorry, not zero energy. Energy 1, but okay, that's a ground state energy. Okay, so okay. But they have they are kind of peaked in these classical orbits. Okay. You want me to show this? No. Okay. Take the maximum of this function. Okay. So you have to take r squared. Well, you take the maximum of this function with respect to r squared, and you will find this. Okay. That's not difficult. Sorry, 2m. Yes? Please. Yes, yes. In fact, they become because you can show that the area enclosed by this surface must be a multiple of the quantum of flux. So an orbit of this type should contain a flux which is n phi 0, where phi 0 is given by the magnetic field. So it's basically is B times the area, okay? So it's B times 2 pi r squared, okay? And so when they increase m, they become closer and closer, okay? They become thinner and thinner, because this each of them should be a multiple of the flux. So in going on one extra flux, then it is a very thin, okay, difference, okay, because you have to do this extra surface will be one flux, so you have 1 equal 2 pi r, and then the distance is 1 over r, okay, or constant, okay. So this distance, it goes to 0. This goes to 0, okay. Yes. Okay. Okay. Now we have the element to understand what I was telling to you, and then we stop. Okay. So we have a picture. We have a picture of the wave function of the lower Landau level. Okay. In space. So I have let me take a radial, and we put r squared, not r, in order to get integer spacing like this, okay? And so what are this wave function? Well, this wave function has Gaussian picked integer value of r. R squared. So this is r squared equal to m, okay? Now suppose that I fill completely the first Landau level, and no electron in the lowest Landau level, in the upper Landau levels. No. So this is in momentum space, but momentum is proportional to r squared, so it's basically the same picture. and here are empty. Okay. Okay. Now, if I have an annulus, it means that the few one here are missing. They are not filled. Okay. So let me remove them. Okay. So any of these peak is an electron. Okay. Okay. Very good. But then I say that this is filled, okay? So this is filled, okay? So this configuration is stable because if I want to make an excitation, I have to I have to put an electron to the lowest lambda level, to the highest lambda level, which is very big energy gap, okay? Proportional to B. So these are kind of maximally packed, okay? So you would say, okay, there are no excitation in this thing. Well, that's not completely true because you understood that. Okay, so this is a ground state with has no excitation in the bulk, because to make an excitation, I will need to go to higher Landau level, and this is forbidden at low temperature. Okay, so there are no fluctuations here in the bulk. No fluctuations in the bulk, or at least they have a very big mass. However, there is something more. There is the boundary. The boundary, the edge. In the edge, in fact, you have to think that this picture of the Landau levels is modified, and you can put, for example, some quadratic potential that allows, that fix, that constrain the particle inside the material. For example, why the particles are inside the material? Oh, because they are attracted by the negative charges of the substrate. Otherwise, the system, I mean, overall, the system is neutral. But if you try to pull an electron out of it, you can, to first order, have a potential which is quadratic. In this potential, the energy level are modified at the boundary like this, quadratically, and like this in the interior. Okay. Suppose you have an annulus, it's in the interior. Okay. So at this point, I have kind of shallow. This is kind of shallow. Okay. So at this point, I'm in a situation in which I have a Fermi level, which is in between the two Landau levels. This distance is very big, so there is no problem doing this. Okay. Okay. So inside here, I cannot make jumps because of very high energy. But near here, I can do particle excitation here, okay? Okay, like this. And they have a small energy. So there are, or the energy on the boundary is of order 1 over r. So the energy on the boundary is of order, due to this confining potential, and it is relativistic to lead in order. So it's something like V over R and, no, sorry, Vn, Vfn, okay? And Vf is of order 1 over R, okay? So you can have these excitations. And in fact, you can show that these wave functions, when you go to region around the boundary, they can approximate it by wave function of a one-dimensional fermion. Because, you see, this is R square. This is R to the M, e to the I m theta, okay? So we said that this is peaked to some region R square of order M, okay? This is peaked. So basically, and once you go to the boundary, when you go to very big thing, we said that the spacing between the different levels become very little. So basically, you can forget about for a very large value of m, which is of order of r square, the size of the annulus. You can neglect this part, the radial part, and so you get only the phase. And this phase is a one-dimensional fermion. Okay? So this system, so we have seen mostly, I mean, pictorially, that the quantum effect, when I fill the first Landau level, I have no excitation in the bulk, but I have boundary excitation, which are fermions, one-dimensional fermions that live on the boundary. So there is one fermion living here and one fermion living here, but they are chiral because basically you reproduce on one side, you reproduce a spectrum which is the positive branch, and on this other side you reproduce a spectrum which is the negative branch. Okay? So the two chirality have been splitted. Okay? And so now you can understand that the Hall current is nothing else than the anomaly current, because you do the spectral flow, you introduce an extra field here, an extra flux depending on time, you produce an electric field longitudinal, and then you move little by little all these states together, and eventually you bring electrons from one side to the other, and this is the Hall current. Okay. So summarizing, in the Hall effect, you have a bulk which is gapful. You have edge excitations which are one-dimensional fermions on the boundary, on the edge, which are chiral on one part, antichiral on the other part, and the current that goes through them is the chiral anomaly. Okay? So in conclusion, the fact that you have this result is the fact that this n is precisely the number that the number of fluxes that you put inside, and in the same as the spectral flow we discussed in the first lecture. Okay. Okay. So what is the advantage to do this? Okay. Well, the advantage of seeing the things like this is to argue that this number, to find the rationale for this number to be so precise, because the anomaly is independent on the property of many property of the system at short distances, so high energy, independence of the impurity, independence of many things, okay? And so that gives you a rationale for such a precision, okay? Which is basically limited by the experimental precision, not by some intrinsic dynamics, okay? This argument that spectral flow is equal to the Hall current was originally formulated by Laughlin. By saying that, by using this theorem that I was telling you before, that Hamiltonian, the so-called, the Young Byers, the Byers-Young theorems. He said, "Oh, look, if I take this field Landau level and I insert a flux, okay, the Hamiltonian with one more flux is gauge equivalent to the Hamiltonian with no flux. The spectrum returned to itself, and simply one electron went from the the inside to the outside. And so I produce the whole current with n equal to 1. And he said, but this is a gauge transformation. So no matter how the Hamiltonian is complicated, this remains true, he said, okay? So basically, was, I think, 82 or 83, I think, Laughlin, 82, I think. Basically, Laughlin rediscovered the anomaly, the argument of the anomaly and the spectral flow by himself, okay? Formulated in the language of non-relativistic theory, so he didn't formulate it like an anomaly, but the idea is the same, okay? Then when you go to discuss the boundary excitation, then you rephrase this problem as the problem of anomaly, the problem of a one-dimensional fermion we have been discussing today, okay? Do I get something else from this? Yes, we will see in the next lecture that I can also discuss in this the effective theory, effective fermion theory on the boundary. I can also describe the case of fractional Hall effect, because in fact it has been found that this number n is not only integer, but sometimes is also fractional. Okay, it's also exact. Fractional numbers are kind of very exact, a bit less exact, but nevertheless are believed to be exact numbers. And there is a way to make sense of these exact fractions in terms of anomalies of the edge theory. So I think that's more or less it. But anyhow, this afternoon I think we have a discussion session, so maybe we discuss more, okay? Questions? Yes? Hmm? Oh, because you know, if you integrate, it's a spectral flow. If you integrate this formula, okay, for one flux, from one quantum of flux, you get a charge which is 1. Okay? Okay? So you get this. So you integrate this. We show the first day that if you transport the charge. So let me explain. Yes. So if I want to do the spectral flow, so I want to make a delta of Q, which is integral in time of Q dot between, let's say, an integral of time, okay? And then we said, okay, this is integral of electric field, and so this is dt of phi dot of t, okay? And so this is phi of t minus phi of minus t, okay? And then we said, look, if we add here one quantum of flux, then this delta Q will be 2. Remember this, no? So delta Q is 2 means that I remove one electron. So I have this. I remove one electron from here and I add it here. Okay? But in the geometry of the quantum Hall effect, this is moving one electron from here to here. And this is the whole current equal to 1. Okay, you see there is the same coefficient. There is an extra, so here is 2 pi, okay? There was a 2 pi here, okay? H bar. There is an extra E that I can tell you why is there, but is that convincing? No. In the first lecture, we said, what is the condition for bringing the spectrum to itself? and then moving one electron from one side to the other. Okay? Okay? This is delta Q equal to 2. Okay? Well, we said because it's possible if this difference is one unit of flux, one quantum of flux. Okay? Now you do the same. Adding one quantum of flux is the same as producing an electric field of this sort, and then you produce this. It's the same coefficient. We will return to this anyhow. There is one more thing to say about this. Please? Yes, yes, it is. It is. Yes, it is increasing. No, but no, you know there are two magnetic fields. There is the external magnetic field, which is very big, and then there is this flux in the interior that you vary in time. That makes this electric field on the boundary. There are two magnetic fields. Yes, it's varying in time. Yes, adiabatically as usual. Okay, thank you very much.